This episode of Real Engineering is brought to you by Brilliant, a problem-solving website that teaches you to think like an engineer. This subject needs no introduction. The entire world is talking about the same thing. COVID-19 has turned the world upside down in just a couple of weeks, and the human race is scrambling to adapt to this new pandemic. COVID-19 is racing through populations. For many, the symptoms are mild. For others, the virus debilitates them. Their lungs' ability to transfer carbon dioxide and oxygen in and out of their blood begins to fall. Each breath becomes more laboured, until eventually they become too exhausted to breathe on their own. The patients that are presenting to hospitals with these symptoms need medical intervention before they suffocate. Unfortunately, we do not have a cure. The best medical treatment currently is to simply assist their lung function with mechanical ventilation, but hospitals are experiencing such huge influxes of patients that they do not have enough ventilators to cope. This has led to a call-out to any and all capable of manufacturing ventilators to join the fight against this common enemy. Medtronic, a company I have worked for in the past, has its primary ventilator manufacturing facility based in my hometown of Galway. Here, they produce this ventilator, the Puritan Bennett 980 mechanical ventilator, a top-of-the-line high-performance ventilator that would give doctors a huge leg up in combating the viral pneumonia that patients are experiencing, but it's a complicated bit of machinery. They currently produce 225 units a week and are pulling employees from the stent manufacturing facility I worked at to help boost production to 500 a week. This, however, won't come even close to fulfilling the demand that is yet to peak. There is an impending doom looming over us that soon hospitals in countries like the US will experience what Italy has already experienced, an overwhelming flood of patients. So, many enthusiastic engineers who want to help out are volunteering their expertise to develop a low-cost ventilator that any manufacturing facility can adapt to build. Every single design I've come across centers around one key bit of technology, a BVM, or bag valve mask. BVMs are plastic bags that a clinical care practitioner can manually deflate with their hands. It's what a first responder would use if a patient wasn't breathing, instead of giving mouth-to-mouth resuscitation. It's a cheap and easy way to force air into the lungs. All these designs are basically just robotic arms that can squeeze the bag at a set frequency endlessly. They, of course, could be manufactured quickly and in great numbers, but ventilators aren't just air pumps that force air into a patient's lungs. One of the primary problems facing doctors currently is managing a side effect of mechanical ventilation, barotrauma. To understand this, we first need to understand how the lungs operate under normal conditions. So let's have a quick biomechanics class on breathing with our sister channel, Real Science.
Two muscle groups typically act to control breathing. The diaphragm, which is a large muscle which separates the abdomen from the chest, and the intercostal muscles, which are the muscles which reside between the bones of your ribcage. When you breathe in, your diaphragm contracts, which causes it to move toward the abdominal cavity, while the external intercostal muscles between the ribs also contract, which lifts the ribcage outwards. Both of these actions increase the volume of the thoracic cavity, the cavity that your lungs reside in. The increase in volume causes a corresponding decrease in pressure, which allows air outside the body at atmospheric pressure to fill the lungs and equalize the pressure. The key thing to note here is that negative pressure drives inhalation. The lungs don't inflate like a balloon. They expand and equalize with atmospheric pressure. On exhalation, the process reverses, with a small spike above atmospheric pressure to push the air out again.
Mechanical ventilation cannot work like this. It has to force air into the lungs from outside the body and essentially blow the lungs up like a balloon. If this is not tightly controlled, the air pressure could work against the diaphragm and the intercostal muscles and end up increasing the pressure in the alveoli above their typical max pressure. The alveoli are tiny thin air sacs in the lung that are in contact with blood vessels to allow oxygen and carbon dioxide to diffuse between the blood and the lungs. To do this, they have to be extremely thin, and because of that, they are very delicate pieces of tissue. Overexpanding them will lead to inflammation at best or rupture at worst. This is what barotrauma is. To make this worse, those suffering from acute respiratory distress syndrome, like those affected by COVID-19, are more at risk of suffering from this side effect of mechanical ventilation, as the alveoli that are filled with fluid prevent air from entering them, causing the pressure to elevate even higher in the functioning alveoli. The last thing we want to do is damage the healthy tissue of a patient suffering from damaged lung tissue. That is the opposite of helping. To avoid this, doctors need to carefully choose their settings on the ventilator. The primary guidance for this is to limit the volume and pressure of air entering the lungs. So, any low-cost ventilator will need a method to control these settings. Designs like this one, which can only vary its volume output as far as I can tell by connecting the push rod closer to the center of rotation of the cam. There is no variable control here. This device would likely do more harm than good. The designer's heart is of course in the right place, but if a YouTuber can spend a day reading a ventilator design book, so can they. However, my patience goes to zero for massive multi-million-dollar companies like Virgin Orbit who present these designs as their own, who clearly have done zero research into what is needed from a ventilator and just built something as quickly as possible to get some positive PR for their company. Look, they even had time to put up a big sign behind them for the video. As far as I can tell, the earliest design that proposed using these BVMs was from an MIT student project from 2010. This paper has been online that entire time, and if people are truly copying it, they're leaving out some clever design ideas that make it more functional. Their design include a spirometer, which measures the airflow rate out of the BVM. By integrating this value over time, they can calculate the volume of air delivered. This then feeds into a controller which can vary how tightly the BVM was squeezed to change the volume of air delivered. This gives the device a nice range of tidal volumes ranging from 200 milliliters to 750. This is a better design and may be useful in a do or die situation, but it is not perfect. The breaths per minute controller is simply set on a time-based frequency ranging from 5 to 30 breaths per minute. This is called a mandatory breath. It's entirely determined by the machine. You will take a breath whether you like it or not. This would obviously be uncomfortable and requires the patient to be heavily sedated to the point of paralysis. But it can also exacerbate barotrauma if the patient's diaphragm and intercostal muscles are resisting the inhalation. High-performance ventilators can work like this, but they typically don't. Their breath sequences are normally triggered by the patient. They are still able to breathe. They just need help because they are exhausting themselves with the effort. In order to do this, the machine needs some way of triggering the breath cycle and ending it too, based on observations of the patient. This can be done in a number of ways. It can be pressure triggered, where a sensor detects a drop in airway pressure, indicating the thoracic cavity is expanding. It can be flow triggered, where a sensor detects airflow into the lungs, or it can be triggered by a sensor detecting electrical activity of the diaphragm, indicating that the diaphragm is contracting to expand the thoracic cavity. This also requires very fast microprocessors to detect and react to the triggers. I have seen no low-cost ventilators incorporating this vital component of ventilator design, and it is a truly vital component. A very difficult part of the ventilation process is weaning people off it again. A ventilator, which requires someone to be sedated to the point of paralysis, makes it very difficult to get them breathing naturally on their own again. There are a multitude of other design considerations to be made with ventilators. I studied biomedical engineering, and there is a heavy emphasis on medical subjects like surgical practice, many of which are taught by doctors, not engineers. The first thing those doctors taught us is to start your design by speaking to the end user, the doctor. I spoke with Rohin Francis, a doctor who runs the fantastic Midlife Crisis channel, to get a better understanding of some of the other things we engineers need to remember when designing these machines.
Thanks, Brian. As you've already heard, COVID-19 patients frequently develop an acute respiratory distress-like syndrome, or ARDS, which not only fills the alveoli with fluid, making gas exchange harder, but also increases the likelihood of the alveoli collapsing shut at the end of every breath out. And this is because diseased areas of lung don't produce surfactant normally. Pulmonary surfactant is a clever substance produced by alveolar cells which coats their inner surface, and one of its key jobs is keeping these tiny sacs open when the lungs are deflated, which is what happens in healthy lungs. But in ARDS, when you breathe out, those alveoli collapse shut, and sometimes whole sections of the lung collapse, called atelectasis. Trying to force them open with every breath requires more pressure and hugely increases the risk of barotrauma. So we use something called positive end expiratory pressure, or PEEP, to try to prevent this. I usually explain this by saying, imagine you've got your head stuck out of the window of a fast-moving car with your mouth open. Don't do this, by the way. In addition to all the insects you'll get in your mouth, you also have a constant air pressure exerted on your airway, making it ever so slightly harder to breathe out, and that is PEEP. PEEP is a constant positive pressure that prevents those alveoli collapsing at the end of each breath, and also helps open up or recruit collapsed areas of lung. In COVID-19, we are seeing patients requiring very high levels and tight control of PEEP to maintain their oxygen levels and protect the lungs, and this is something that a basic bag-squeezing vent cannot really achieve. From the mechanisms I've seen so far, I'd be very concerned about the possibility of baro and/or volute trauma. Most of these patients are on a ventilator for a few weeks at the moment, and a basic bag squeezer might be adequate for the first day or so when a patient is deeply sedated, but simply won't work as you try to ease off the sedatives. Additionally, your upper airways warm and humidify air entering the lungs, but they're taken out of the equation by the endotracheal tube, which goes directly into the lower airways. Without the warming and humidifying features of modern ventilators, lung tissue will get rapidly damaged. This isn't even a ventilator, it's an anesthetic machine, because the ventilators I was going to film with are in use right now. And even this big thing can only provide very basic ventilation. And while we do need more ventilators, what's even more valuable are the intensive care nurses and respiratory therapists needed to work them, but they take significantly longer to produce.
So, as you can probably tell, there is a lot more to ventilation than just pumping air into a patient. Tight regulation of pressure, volume, oxygen percentage control, and humidification would all require more complicated mechanics than these simple BVM pumps. Designing a ventilator fit for purpose with cheap and easy to manufacture components is a difficult job, but I'm positive a viable product will come to light soon, especially as this is not a new problem. Poorer countries have been struggling with the lack of cheaper medical supplies for years, and there are products like this one from an Indian robotics engineer, which uses an Android phone as the user interface. It was on the market long before this pandemic started and was designed to help poorer families treat their loved ones at home, so the need for trained medical personnel to run it is lower too. I can find very little information on its capabilities, but the company has received massive orders from the Indian government already. Unfortunately, India has banned all export of medical devices like this, but its manufacturer is licensing the design. We are all in this together, and I hope this video doesn't come across as a teardown of well-intentioned engineers trying to help. It's much easier to point out the flaws in a design than to actually put in the time to design something yourself. This is just an attempt to point people in the right direction. Inspiring future generations of engineers is the mission of this channel, which is why I partnered with today's sponsor, Brilliant. Many people are on the lookout for online math and science resources right now, and whether you're a student looking to get ahead, a professional brushing up on cutting-edge topics, or someone who just wants to take some time to understand the world better, you should check out Brilliant. You've already seen that there is a lot of physics and engineering that go into designing medical devices like ventilators, and Brilliant has excellent courses that unravels the interesting physics in the world around you called Physics of the Everyday. Inside, you'll learn things like how the behavior of an expanding ideal gas is used to build a refrigerator, and how the energy requirements of the muscles in your body scales with the body size from mice to elephants. You can set a goal to improve yourself and then work at that goal a little bit every day. Brilliant makes that easy with interactive explorations and a mobile app that you can take with you wherever you are. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new every day. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with their interactive explorations, and over time, you'll be amazed at what you can accomplish. As always, thanks for watching, and thank you to all my Patreon supporters. If you'd like to see more from me, the links to my Instagram, Twitter, subreddit, and Discord server are below.